Hello guys, welcome to Meg Misra channel. So today we are going to understand a very important mechanism, that is brittle fracture. So let's start without any delay. So first of all, the basic understanding of the brittle fracture. So prior to that, I'll give certain interesting thought. So this is a older incident. Everyone heard the sinking of the Titanic ship. So we have a movie on this also. So the thing which I want to mention here is why Titanic is related to the brittle fracture. So the sinking of this Titanic was caused primarily by the brittleness of the steel which used under construction of the hull of the ship. So this portion we are calling hull. So this portion of this Titanic's this ship was made of by steel, and this steel become brittle when it was traveling toward the ocean. So in the icy water of the Atlantic, the steel was below ductile to brittle transition temperature. Okay, so there is a ductile to brittle transition when material from ductile to become very brittle like glass. See here, this is a brittle glass. By sudden impact it can break in pieces. So at lower temperatures the material become like this glass, and any impact on the material, the material get rupture and break in the pieces. So that's happened with the Titanic when it was traveling through the ocean in icy water of the Atlantic. The impact of an iceberg. So what is iceberg? This is iceberg. This is a mountain of ice which get formed in the ocean. So the Titanic, which was running in icy water, and that got contact with got impact, means there was a collision between this Titanic and with iceberg, and the ship hull resulted into the brittle fracture of the bolts that were holding the steel plates together. So this hull, which was holded by the steel bolts, that got fractured, and this Titanic broken in two pieces. So this is how we people later known after this incident the importance of the brittle fracture. So basically material behaves like a brittle as glass at lower temperatures, and any impact on at that temperature the material will break into the pieces and behave as a brittle material. Okay, so now let's stand at the brittle fracture. So brittle fracture is the sudden and rapid fracture under the stress, that is residual or applied, where the material exhibit little or no evidence of ductility, because under this is a sudden phenomena, and when this happen material's ductility get lost. There is a plastic deformation. Although rare in refinery operation, in service brittle fracture of a pressure vessel or other pressure can have serious consequences. So okay, so the loss of toughness is a brittle fracture. So basically most susceptible metal are carbon steel and low alloy steel are prime concern, particularly the older steels. Okay, so this is the failure of a vessel. You can see this fracture which got failed due to the brittle fracture. There is a sudden failure, sudden loss of toughness at lower temperatures. The brittle fracture can occur in potentially susceptible piece of equipment containing a flaw or other stress concentrator. So if there is a flaw, that will give a path for brittle fracture to occur. So there are three primary factors for brittle fracture. First is materials fracture toughness, okay, which we check by the CHARPY test. We do impact CHARPY test as suggested by code. Then size and shape of the shape and stress concentration effect of the flaw. What is size, shape? And third is the amount of the residual stress applied on the flaw. So these are the three critical factors which will govern the brittle fracture. Now we will understand ductile versus brittle. So when we do this tension test, means we provide tension to a piece of wire or piece of rod, then if material is ductile, it will break in like this. It will first expand, then at the end it will break. So for ductile, the stress versus strain curve go like this. So from up to here, stress is directly proportional to strain and material will regain its position, but after this point material will fail and it will it will drawn into the wire and it will go like this, and at the point of B the material will get fail. Okay, and area under this curve is we are calling the toughness. So what is toughness? Is ability to absorb the energy up to fracture. It is the total area under the stress versus strain curve. Okay, so this is a ductile failure, ductile material. Now moderately ductile, it will somehow it will drawn into wires and later it will fail in cone and cup type profile. So this is moderate ductile, and when a material is brittle, it will not draw or it will not lose its area, it will suddenly get break. So this is a curve of the brittle. So brittle material, when we apply the stress, it will go up to here, stress versus strain, and it will directly fail. And the area under this curve is give the toughness. So the area of brittle curve is very less, means toughness of the brittle material is very less and toughness of the ductile material is more. So this is a toughness of ductile material. So necking will occur in this ductile materials, but in brittle there will be no necking, it will directly fail. So here also area under the curve is energy absorbed. So for brittle it will directly fail. For ductile it will first be produce necking, and after necking the material will get fail. So see, if I have applied the tension, this is A is a brittle, B and C, this is a moderately ductile, this is highly ductile, and see this is a brittle type failure where we cannot see any necking, but here we can see the necking. First it will get drawn into wire, then it will break. So A is brittle fracture, B is ductile fracture, and C is completely ductile. So that's the difference between brittle and ductile, and the area under this curve, stress versus strain curve, is toughness. For ductile there high toughness, and for brittle it is lower toughness. Okay, so that's what is the understanding. Now what are the critical factors for the brittle fracture? So the susceptibility of the material to brittle fracture may be increased by the presence of the embrittling phase. If there are embrittling phase, the susceptibility increase. Also the steel cleanliness, means the chemical impurities in the metal like level of sulfur, phosphorus and other impurities, and the grain size has significant influence on the toughness and resistance to the brittle fracture. So microalloying elements like vanadium, Nb, boron, titanium, certain ranges, as well as sulfur, phosphorus, manganese above their residual limit can cause low toughness. So if these are more than their limit, that will cause the lower toughness. Then the heat treatment condition of the material can affect its toughness, fracture toughness. The thicker material section have inherent lower resistance to the brittle fracture. So thick material will fail first by the brittle fracture. They have lower toughness. In most of the cases, in material that exhibit ductile to brittle transition, the brittle fracture occurs only at temperature below the Charpy impact transition temperature. So there is I have told ductile to brittle transition temperature. So below that temperature, material will fail. So this there in a code like section net division 1 or ASME B 31.3, this curve, this is a impact exemption curve, is mentioned to decide whether impact testing are required or not. So equipments manufactured to ASME section 8 division 1 prior to December 1987, this requirement was not there. Okay, so this notch toughness requirement was not there, but equipments which were made later 1987, this requirement came into the picture. So equipment made same code after this date will subjected to the requirement of UCS 66. So this article, this section UCS 66 is very important, whether we require the impact test or not to check the toughness. So to check the toughness requirement at lower temperature, this impact test is done. Most process run elevated temperature, so the main concern of brittle fracture during startup and shutdown or hydro testing. So this is telling that most of the process run at higher temperatures, but this brittle fracture can occur in case of startup, shutdown, or in case of hydro testing. The thick wall equipment, in particular any unit, should be evaluated. Thick wall equipment in particular unit should be evaluated. So what are the thick wall equipments that should be evaluated for the brittle fractures? Now how we can confirm that whether my equipment require this impact test or not? So as per code, they has classified equipment as per curve A, curve B, curve C and curve D. So you can find out the list of equipment which governed by curve A, curve B, curve C, curve D. So this curve is thickness. This is a thickness versus the temperature. So we have thickness given and temperature given. So if I am dealing with curve D and my thickness is 25 mm, means 1 inch, and temperature is 30, then if I am falling on this curve or below, the impact testing is not required. But if I am falling anywhere above this curve, then impact testing is required. Okay, so if I am below this curve, impact testing is not required. I am above this curve, impact testing is required. So that's how we need to check whether if I am operating at the lower temperatures, my material should be impact tested for to confirm that if there is a chances of brittle fracture. So hope you have found this video useful. Thank you very much.